So yeah, as Andrew mentioned, I think we maybe have the lengthiest title of this whole conference, but this is work done to do some archival radial velocity analysis, so a little lower precision than much of what we've been hearing about today. Well, I'm the one up here speaking. The majority of this work was actually done by a former JPL intern and then thesis student, undergrad thesis student, who worked with myself and Eric Mamajek, named Catherine Laliotis. She's not here because it turns out that when you give someone their very first science project and then have them write a 50-page paper studying 50 stars, they run away and become a cosmologist. So Catherine is now a graduate student at Ohio State University and studying cosmology. But when I told her we were having this conference and that it was set in Santa Barbara, she sent me a location appropriate photo so we could pretend that she's here in the room with us. We also had a variety of wonderful co-authors who helped us with this effort, and many of whom are in the room. So thank you again for all of your assistance. Okay. So NASA's, the 2020 astrodecadal report main recommendation for exoplanet science was that NASA should embark on a program to realize a mission and search for biosignatures around roughly 25 Earth twin planets. Okay. The idea for how we're going to do this is it'll be a large next flagship mission, and we'll do direct imaging from space. And it turns out that because of the technological challenges that come along with high contrast direct imaging, the stars that we are able to look at are relatively limited. We need stars that are nearby and bright so that we have both the spatial resolution such that a planet in the habitable zone of that star is outside the inner working angle of the coronagraph on the mission. And the stars need to be bright enough that there are enough photons coming off that planet such that when we block out the starlight, we can actually get a signal of the planet itself. And so the Exoplanet Exploration Program Office, Eric Mamajek and Carl Stoppefeld recently released an updated target list for this mission. And you can see here there are something like 160 stars on that list. All of them are within 25 parsecs, and the faint stars on this list are up at about 7th magnitude. So very bright, very nearby. Now, there's a little bit of a concern because if we need to get to 25 Earth twins, 160 stars isn't the biggest list to start with. But again, we have these very strict physical constraints. We don't know Eta Earth super well yet, and so we are curious about how many Earth twins might exist around this population. We're also wondering about how many temperate non-Earth-like planets could exist around these stars. Specifically, could there be temperate giant planets orbiting around these stars that would dynamically preclude the existence of an Earth twin? And so this is a nice simulation done by Sarah Milholland at MIT that shows if you put a slightly eccentric Jupiter-sized planet around a sun-like star, which is the black orbit here, it dynamically eats up the majority of your habitable zone. So the habitable zone are between these two concentric green dashed circles. The red area is where you can't have any other planets because this Jupiter would have destroyed them already. If we generalize that a little bit and look at how the stability varies as a function of both planet mass and orbital separation, you can see that Jupiter, even at a half Jupiter mass planets, anywhere near the habitable zone really brings the fraction of the habitable zone that's stable down to at least 40%, if not all the way down to 10 or so. And that's especially concerning because work from BJ Fulton a couple of years ago told us that massive planets are quite common in the habitable zones of nearby stars. So we expect that a decent fraction of this target list may actually just not be conducive at all to hosting Earth twins. So the question we wanted to answer was, well, what can we already say about the habitable zones of these stars based on archival radial velocities? Because the restrictions that guide the target list formation of a direct imaging space mission mean that we're looking at bright nearby stars. And if we want to look for Earth twins, we're looking at solar-like stars. And those adjectives map pretty closely to the stars that have been preferred for radial velocity surveys starting all the way back in the mid-90s when we started doing precision RVs. So what we did was combine archival data from the Planet Finder spectrograph on Magellan, high-res on Keck, the UCL spectrograph that is now decommissioned but used to be on AAT, the APF, and the HARP spectrograph at Lucia. And this was really prompted by the publication of a lot of archival HARPS RVs in the RV Bank online archive by Trifon Trifonov. And so our HARPS data is pulled from there. The S indices that we use are adapted from some work by Volker Perlowitz that he did for Carmenis. And then the other instruments, we were working directly with the team, so we have input from them. Okay. So again, here are the existing epochs of RV data for these stars. You can see that many of these stars have dozens, if not hundreds, of existing RV observations in these archives. And so What we did was, if you want to understand the mass sensitivity that you already have in the habitable zone of a star, you need to actually work not with the original RVs, but your RV residuals once you fit out any signals that you think are in there. And so we did this using Radial and RV search to perform iterative, uninformed searches of the RV time series and then perform injection recovery studies. And so along the way, we revisited some old favorites. So this is HD 115617 or 61 Ver. The original paper on this system came out in 2011, so it was published here, and found 3 planets that looked beautiful even back then. You can see that there's a significant amount of additional data that has been taken in the intervening decade, but this system hasn't been revisited. Okay, that's not true. Lee Rosenthal included it in his paper a year ago, so he beat us to the punch. But until then, it hadn't been revisited for almost 11 years. When we look at how the data has evolved with time, we see that there are still 3 beautiful sinusoids that pop out, so in good agreement with the original paper. And indeed, that the error bars on the orbital parameters get a bit better. And this is true for the majority of the stars that we look at. So this figure here shows the ratio of the error bars for the period, eccentricity, and semi-amplitude. And so anything that is above that gray dashed line is a planet where the errors got better. Anything that is above the green dashed line is where the errors got better by a factor of 2 or more. And there are some planets below that. That's generally cases where their stellar activity management in the original publication was more sophisticated than what we did. Because indeed, our approach to activity, because this was such a large project with so many systems, was quite basic. We do a simple period comparison between signals we see in the radial velocities and signals we see in the S indices, or for UCLs in the H alpha data. We struggled a little bit with how to combine the S index data, especially the errors for the S index data, because you can calculate a photon error for an S index, but those values ranged a lot between the instruments in a way that we felt was not really representative of the sensitivity. The S index isn't really photon noise dominated, it's more systematics dominated based on how you continue to normalize your data and things like that. And so what we end up doing is taking a set of 6 stars that are observed across all the instruments, calculating the RMS after we've removed any significant signals, and then we assign an instrument-specific error that we apply to all data from that instrument. Given that all of these are very bright stars and they're similar spectral types, we think this is not a great solution, but an acceptable one for putting things into a common reference. In addition to revisiting some old favorites, we also found some new candidates, which is exciting. So this is a system where there are 2 very large, very long period signals at years to decades, and then 1 much shorter period signal. If we look, so this is the period comparison I was talking about. If we look at the periodograms from the S index data, you can see not exact matches, but very close matches for those long period signals. So we think these are probably 2 stellar cycles that are going on within the star. But notably, we don't see anything that's akin to this 10-day signal, or sorry, 20-day signal that we see in the radial velocities. And so this is now a signal of interest that we're doing some follow-up work on and trying to see if it holds up as a real planet when we dive in more carefully to this system. And then we also end up disputing some known planets. So this is HD 85512. There was an original publication in 2011 that had a period detection of 58 days. Our updated analysis that has, again, a decade or more data in it has a period of 51 days. Those are, given the error bars and how precisely we've measured the period, those are a 50 sigma offset, which seems unexpected. And if you create a rolling periodogram of the data, you can see that for the first 10 years, there's a beautiful 58-day signal that is bang on steady, looks very reliable. And then right after that paper was published, that signal bifurcates and becomes 2 separate signals at 60 and 57 days or so. And another stronger signal shows up down at the bottom here at around 51 or 52 days. And so we think what looked very sensibly like a planet back in 2011 is actually stellar variability. And so this is a good reminder that we should keep an eye on signals, even ones that seem well vetted, just to make sure the stars aren't being extra tricky. Okay, so back to our original goal. The whole purpose of this was to get to RV residuals, and then it took us like 2 years of work to fit all the systems appropriately and feel like we had done a decent job to get to the residuals. But once that happens, we want to, again, ask what we can already say about these stars and try to quantify the mass sensitivity at each star's Earth equivalent insolation distance, or EEID, i.e. the distance from the star where a planet would receive the same amount of light that the Earth gets from the sun. And so you take the RV residuals, you inject thousands of synthetic planets, and then our research does this very nice job of telling you which of those planets are successfully recovered, those are the dots in blue, versus which ones are not recovered, the dots in red. And then you can calculate the EEID of the star and say, at that distance, what is the 50% mass probability for detecting the planet? And so in this case, for this star, the mass sensitivity is about 48 Earth masses, which isn't terrible. But it turns out that for many of these stars are going to be the priority targets for NASA's next flagship mission. We actually can't say much at all yet about the mass sensitivity or what planets might exist in their habitable zones. So this plot shows for each star the mass sensitivity at that Earth equivalent installation distance. And what we find is that for the majority of the stars, we are not yet sensitive to Neptune mass planets, which would be physically disruptive to an Earth twin. So even though these stars are in many cases wonderful RV targets, we just haven't looked at them with the cadence or sensitivity necessary yet to really probe these habitable zone orbits. Okay, so takeaways as I'm down to a minute. There's a lot to be gained by taking the time to try and combine archival radial velocities, even ones that have uncertainties at the 2 or so meter per second level. We get better orbital parameters for known planets. We sometimes find cases where known planets turn out to be stellar variability, and we sometimes find new candidates. So there's a lot of benefit here. There's still this question of how to better combine the S-index values, and if anyone has thoughts on this, I would love to talk to you about it. And also, we think we need a more sophisticated treatment of activity as we dive further into these stars. And our current mass sensitivity for these Southern Hemisphere habitable worlds observatory targets is not great yet. And so I think there's a lot of benefits and strengths to starting new precision RV surveys with existing instruments that can then provide roadmaps for when we eventually have higher precision instruments, we can chase very specifically the systems that are the most promising. Okay, and with that, I will say thank you so much for your attention and ask for any questions.
Ansgar.
Thanks, Jen. Great talk. For the system where you see the two periods, the one 50 days and 60 days, if I got it right. Maybe you want to check whether the beat period between the two is close to 1 year. I think this is the case. We see a similar thing in Barnard stars, so we can't really rule out that there is something happening with the detectability of some signal that may be a planet or something else and activity going on, and that if the beat period is exactly 1 year, that might destructively interfere with the detectability over some period.
Ooh, noted. Okay, I am going to come find you at a coffee break, but that sounds very interesting.
Thanks, Jen. Great talk. At what point should we just be waiting for Gaia to tell us astrometrically where the giants are? And at what point should we just be saying we should not wait, we should just follow this up?
No, that's a great question. I don't have this figure in here. It just went into a proposal I wrote. So Gaia DR3 is not sensitive to things below about a Jupiter mass. Even for Gaia DR4, my understanding is that we expect the sensitivity to be, a Jupiter or half a Jupiter mass, but at longer periods, because you need the bigger lever arm for the astrometric signal to be big enough. And so I think Gaia is going to find us Jupiter analogs, which is maybe even more encouraging, because then we should focus on those systems and see if we can then hunt inwards to find something like the Earth in a architecture like our own solar system. But I don't think it's going to find us the Saturn or Neptune mass planets in the habitable zone. So it really is, RV is like the way to do this, and maybe the only way to do this.
All right. Let's thank Jen one more time.